Right, so before we dive into the wonderful world of differential equations, there's a few small matters that we need to discuss. So, in my notes, I put a chapter 0. This chapter 0 is not included in the textbook, but I felt like there needs to be some kind of introduction before we get right into it. So, first of all, Calculus 3 is not a prerequisite for this course, which means that anything from Calculus 3 that we might need, I'll have to explain to you. And so that's exactly what I'm going to do right now. The main thing that we need to know for right now is that you can have a function of more than one independent variable. So, in single variable calculus, you give me y as a function of x. This means that every value of the dependent variable y is completely determined by the value of the independent variable x, and that's it. And, you know, there were plenty of examples of these. We had like y equals e to the x. You put in x, you get y out. You had y equals x squared divided by the arctangent of x. Again, you put in x, you get y out. Nothing really special here. Now, what we need to keep in mind, though, is that it is possible to have a function of more than one variable, more than one independent variable. In that case, you'd have something like z equals f of both x and y. This isn't that much different. It's just saying now you have to tell me what both x and y are in order for me to get a specific value for z. So, of course, these functions could look like whatever. You could have something like x squared minus y squared. As you can see, in order to figure out a value for z, you're going to need a value for both x and y. You could have something like z equals y over x. Again, you'll need a value for both x and y in order to determine a value for z. You could have something like z equals x natural log of y. And again, we need both x and y in order to uniquely determine z. Okay? And the truth is you can come up with a function of as many variables as you like, but in this class and also in Calculus 3, usually that's just like 2 or 3 variables. And there's one more thing that we need to discuss about these. It's the concept of a partial derivative. So, if I give you a function that looks like y equals f of x, and I ask you for the derivative, hopefully you know what that means at this point. You recognize that, okay, we've got to take the derivative of this function, which you do the same way that you did in Calculus 1, and then whatever that is, that tells us how y depends on x, right? Or at least that's part of the information that it gives us. Okay? Similarly here, you'd like to know how the dependent variable z depends on both x and y. Okay? So in this case though, we've got a little bit of a problem. If I asked you what's the derivative of like z equals xy minus y, well, with respect to which variable? You see the problem? You could be talking about the dependence of z on x, or you could be talking about the dependence of z on y. So for this reason, we have what's called a partial derivative of z with respect to x, and a partial derivative of z with respect to y. And as you can see, these this isn't just my handwriting. Like this is an actual different symbol than this D. Okay? Now the way that you compute these is very simple. You just have to, well, it's very simple once you get the hang of it. You have to imagine as though the other variables were held as constants. So let's look at Z. What we're going to do is imagine that Z is dependent on X and Y is just a constant. Okay? Well, in that case, we'd have something like, all right, 5 times X, the derivative of that would be just 5. So this is going to be like the constant minus derivative of a constant is just 0. So the partial derivative of Z with respect to X is Y. Then you could talk about the partial derivative of Z with respect to Y, and in the same vein, we want to consider X as though it were constant. Okay? You take this derivative with respect to Y, what we'll get here is X minus 1. Because the derivative of xy with respect to y would be just x. Derivative of y with respect to y is 1. Okay? And let's just do one more example so that we're clear on this. You could have a function of 3 variables. You could have something like f of x, y, and z is x squared y plus x, like z over y minus the cosine of xy plus z. Again, this is a function. Its independent variable f is determined by its dependent variable f is determined by 3 different independent variables, which are called x, y, and z. Okay? And you can take the partial derivative of f with respect to x. You can take the partial derivative of f with respect to y. And you can take the partial derivative of f with respect to z. These are all valid things that we can consider. So with respect to x, if you imagine that z and y are just constants, and you're taking the derivative of this thing with respect to x, we have, let's see here, 2yx, so 2xy, plus, okay, this doesn't have an x in it at all, so the derivative is 0. And then minus cosine, okay, so we're going to have to use the chain rule here. So we'll get positive sine of xy plus z. And then according to the chain rule, we have to take the derivative of the inside. So the derivative of the inside with respect to x is just y. So we just get that. With respect to y, the derivative is x squared minus z over y squared plus the sine of xy plus z times x. And with respect to z, the derivative is 1 over y plus the sine of xy plus z times 1. Now these functions of several variables are the topic of Calculus 3, and you'll discuss much more interesting things about them than just partial derivatives. But for our class here, differential equations, this is about all we'll need. Just what a partial derivative is, it's just describing the dependence of the dependent variable on the independent variable, and how to compute it. Okay? So with that, let's get into the next part of Chapter 0's introduction, which is discussing what exactly a differential equation is. So you can think of it like this. A differential equation is any equation where one of the operations involved is differentiation, taking a derivative. So in your mathematical career, you learned about many different types of equations. You learned how to solve equations that look like x plus 2 equals 0, probably very early on. That was pretty easy for you, probably. And then you got a little bit harder. You included multiplication. And then you got a little bit harder. You started talking about quadratic functions. So now you might introduce the possibility of raising to an exponent. At some point you probably talked about exponential functions. So if you had something like that, you could probably solve it. And so on, right? You had all sorts of operations involved in making an equation. In this class, differential equations, all we're saying is, okay, the equations that we're going to be considering have the operation of take the derivative in them. So for example, you could say dy dx equals x squared, and you'd be asking, all right, I want a function whose derivative is x squared. Okay. So that's all that's going on here. We're just now describing equations that have derivatives as one of the operations. Now, there's some more in my notes about classification, and yeah, I think I'll get into that. So, classifying differential equations is actually extremely important. By classify, I mean come up with a term for a type of differential equation that's unambiguous. Why is this so important? Well, the reason why is because when you dealt with just algebraic equations, usually the strategy was always just get the variable by itself on one side of the equation and then you're done. Okay? With differential equations, the process is much more difficult. There is no single strategy that will tell you how to solve any differential equation in existence. This should be reminiscent to you of a previous class, Calculus 2, where you had things like integrals. You had things like ln x over x. And you had things like x squared e to the x. And things like 1 over x squared plus 5x plus 6. How do you solve an integral? Well, it depends on what the integral is, right? And for that reason, we had names for the techniques that you use for them. This one would have been done by what we call U substitution. And this one would have been done by what we call integration by parts. And this one would have been done by what we call integration by partial fraction decomposition. So similarly here, if you just try to ask, how do you solve all the differential equations? You won't get anywhere because there's no single strategy for it. We need to classify to a smaller subset of all the differential equations and focus on these classifications one at a time. Okay? And so that's how this class is going to be structured. Now, the first step in classifying a differential equation is whether it is ordinary or partial. Okay? So, differential equations, we have ordinary differential equations, and then we have partial differential equations. Ordinary differential equations, okay, these are differential equations that have only one independent variable. So only one independent variable. On the other hand, partial differential equations, these have more than one independent variable. Okay? And the reason why they're called partial differential equations is because they have partial derivatives in them. So let's look at some examples of each of these. So ordinary differential equations, you could have something like y prime equals 3x squared plus 5. Okay, this is an ordinary differential equation because because x is the only independent variable here. Once you have x, you have a value for y. And it's a differential equation because it's saying I want the functions y whose derivatives are 3x squared plus 5. Okay. And then on the other hand, let's look at a partial differential equation. A partial differential equation might be something like second partial derivative of f with respect to x plus second partial derivative of f with respect to y plus second partial derivative of f with respect to z equals 0. That one's a lot harder. This is called Laplace's equation. And it's a lot harder because now you don't have just x, you have x, y, and z. And f, your solution, is depending on all of them. Okay? Another example of an ordinary differential equation would be something like y prime equals 2y. This is asking for all the functions whose derivatives are twice those functions. Okay? And the idea here is that y is only dependent on x. It's not dependent on any other independent variables. Another example of a partial differential equation could be something like partial u partial t equals partial squared u partial x squared. Again, harder, and again, a partial differential equation because u depends on both t and x. That's called a heat equation. Not that you'll need to know that necessarily. Okay. And then we could have an ordinary differential equation that looks like d squared x dt squared plus 9x equals 10 cosine of 2t. All right, that's a little bit harder than the previous two examples of ordinary differential equations, but again, the theme is the same. X is the dependent variable in this case. T is the only independent variable, okay? The only variable that x depends on. Okay? And then as another example of a partial differential equation, you could have the Schrödinger equation, which looks like, well, I h bar partial psi partial t equals negative h bar squared over 2m partial squared psi partial x squared plus v psi. And this thing is a mess. It might look like a mess to you because h bar is a constant, I is a constant, m and v are supposed to be dependent on the system that you're working with, so they're constants as well. Psi is supposed to be the dependent variable here. It depends on both x and t. Okay? So, if this side is intimidating to you, you're not alone. And in fact, we will not be dealing with partial differential equations in our class. Our class will only be about ordinary differential equations because these things are a class in and of themselves. You can find a class here named partial differential equations. You can find more than one class at this university named partial differential equations, and that's what their topic is about. For us, we're only concerned in this class with one independent variable. Okay? Now, the next step in classifying ordinary differential equations is what is the order of the differential equation. So, next up we could have order. Well, you can have as high order as you want. So you could have first order, second order, third order, and you know, there are infinitely many more orders that you could have. What does this order mean, though? It's the highest derivative. It's the highest derivative on which the equation depends. Okay. So what I mean is, just giving some examples here. Y prime equals the square root of x plus y. The highest derivative being taken in this equation is a first derivative on the left-hand side. So this is called a first order equation. You could have higher order equations like y prime prime equals x over y. So this is saying the second derivative of y needs to be x over y. That's a second order equation because the highest derivative being taken is a second derivative. You could have y prime times y equals the sine of x squared plus y. Again, the highest derivative being taken is a first derivative, so this is a first order equation, first order ODE. You could have something like y prime prime times y plus y prime squared equals 0. All right, now you're taking the first derivative and the second derivative, but the highest of those two is the second derivative. So the order here is it's a second order equation. And you could have something like a 19th order equation. That's fine. That would look like maybe y 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 equals, I don't know, anything, x. So this is a 19th order equation. Why? Because the highest derivative that you're taking is the 19th derivative. Okay? So, I hope you'll agree with me that this is an eyesore. And it's not particularly easy to read either. So we have a notation for when a derivative is higher than third order. An exponent with parentheses around it. That's a lot easier to read, right? Okay. And we can look at some more examples. Just classifying ordinary differential equations by their order. So if you have a fourth derivative of y plus y prime prime plus y equals e to the x, the highest derivative being taken there is a fourth derivative, so therefore this is a fourth order ordinary differential equation. Again, all of these are ordinary differential equations because they're all just y depending on x and no other independent variables. You could have a third order differential equation that could look something like third derivative plus x squared second derivative plus x first derivative plus y equals 0. This is a third order ODE. You could have something crazy like 1 over y prime prime plus 1 over y prime plus 1 over y equals the arctangent of x. Again, the highest derivative being taken here is a second derivative, so this is a second order ODE. And you could have something like 100th derivative of y plus y prime equals y to the 200th power. That's a 100th order ODE because the highest derivative you're taking is the 100th derivative. This is not the 100th, this is not the 200th derivative of y, this is just y raised to the 200th power. So this is a 100 order ODE. And so on. As many derivatives as you can take, that's how many order ODEs there are. Okay. Now, there's one more thing I want to mention before we get into what the book calls the first chapter. In this class, whenever we're asking for a solution to an ordinary differential equation, we're always asking for a function, okay? So, for an algebraic equation, in the past, you had something like 5x minus 10 equals 0. And you solve this by adding 10 to both sides, and then dividing both sides by 5, and then you get x equals 2, and then you're done. That's the answer, right? So that's the answer to the question of what real numbers satisfy that 5 times that real number minus 10 is 0. Okay? In our class, we don't want just a real number as an answer, though. Okay? Because sometimes we're dealing with a situation that requires more information than that. So, like, for example, suppose you have a differential equation that describes water being poured out from a vessel. If you just give me a number for how many liters per minute is being leaked out of that vessel, okay, but then I'm going to ask, is it constantly that much, or does it change over time? And you just need to think about pouring water from a vessel for a minute to realize it's not going to be constant. It is going to change over time. And so therefore, it would be better if you could give me a function of time that describes how much water is leaking from the vessel. So for us, when I give you something like y prime equals 1 over x squared plus 1, for instance, I'm not looking for just a number. Okay? Just a number would be insufficient. What we want is a function whose derivative is 1 over x squared plus 1. Okay? And with all that said, I think we are ready to get into our first chapter. So 1.1, this is integrals as solutions. So let's take a look at this thing right here. We're asking what function has a derivative of 1 over x squared plus 1. Well, if you think about that for a second, you realize that this is the same as asking what is the antiderivative of 1 over x squared plus 1. And so you had a way of doing that in Calculus 2. You took the indefinite integral. Now, this one can be done by trigonometric substitution, but it's much easier to just remember that 1 over x squared plus 1 is the derivative of the arctangent of x. Okay? So in Calculus 2, you would write this is equal to arctangent x plus c. And what is that c? Well, that c was just an arbitrary constant. In other words, you can make that c anything you want, and then this is still going to be a antiderivative of 1 over x squared plus 1. So you've given me quite a lot of information here. You've not given me just one function. Actually, you've given me a family of functions, all determined by this c. And they're all the functions that satisfy this condition that their derivative has to be 1 over x squared plus 1. Nice. This family of functions that describes all of the solutions of an ODE is called a general solution. Now, if I just want one function that satisfies my ODE, in order to distinguish that that's just one function and not a family of functions, we have another term for that too. That's called a particular solution. Okay? So this is the general solution. It's this arctangent of x plus arbitrary constant. And in general, every general solution is going to have at least one arbitrary constant in it. Okay? That parameter will tell you which function you're talking about when you have a group of solutions of an ODE. Okay? So when you have y prime equals f of x, this always works. You always just find the general solution by taking the indefinite integral of f of x. And that's it. What this means is that all of the work that you did on solving indefinite integrals in Calculus 2, if you rephrase it a little bit, you realize that what you did there was just solving differential equations with the form y prime equals some function of x. Okay? And for today, that's all I need you to understand. And we'll do a few examples. So, Let's suppose we have y prime equals x to the third. Pretty simple stuff we're starting out with. We want to find all the functions whose derivatives are x to the third. In other words, we want all of the antiderivatives of x to the third. So, we have a name for the set of all the antiderivatives of x to the third. That name is the indefinite integral. So we're just taking the indefinite integral of x to the third. And hopefully we all remember from our mathematical experience that the way to take the antiderivative of x to a power other than -1 is to add 1 to the exponent and then divide by the new exponent, right? So this just becomes 1/4 x to the fourth plus c. And that right there is the set of all the functions that satisfy this ODE. It is our general solution. Okay? Now there's one other type of problem that we'll be concerned with in this class. Not just finding general solutions, but also finding particular solutions that satisfy additional conditions. They'll be called, those sorts of problems are going to be called initial value problems. So for right now, these look like a differential equation together with some point that has to lie on the graph of the solution. So like y of a equals b. Let's look at an example of one of these problems. So together, the differential equation with the condition is called an initial value problem. And we're going to look at an example now. So suppose we have dy dx equals x squared plus x with the condition that y of 1 has to be 3. So these two things together form an initial value problem. Okay? We are not looking for all the solutions of this ODE. We are not looking for all the functions that satisfy this first condition. We're looking for all the functions that satisfy this condition and this condition. Okay? So not just the general solution, but rather a particular solution. And not just any particular solution, the one that satisfies this condition. I feel like I'm talking in circles at this point, but the point is, this is just one more step. After you find the general solution, you just have to use this condition to figure out what c has to be. Okay? So in our case right here, we have y equals the integral of x squared plus x. And then that turns into y equals 1/3 x cubed plus 1/2 x squared plus c, where c is an arbitrary constant. Okay? This is our general solution. But we're not done yet. We're not done yet because not all of these functions satisfy the condition that y of 1 has to be 3. So we have to do one more thing. 3 equals y of 1. I think we can agree that that's just a rephrasing of the problem. And then according to our general solution, that's going to be 1/3 1 cubed plus 1/2 1 squared plus c. All right, and then we have now an equation that we can solve for c. And when we do that, we'll have our particular solution. So 3 equals 1/3 plus 1/2 plus c. 3 equals, let's see here, 1/3 is 2/6, and then 1/2 is 3/6, so this is together 5/6. So then c is going to be, let's see, 18/6 minus 15 minus 5/6 is going to be just 13/6. That tells us what c is. So the particular solution that solves our initial value problem is 1/3 x cubed plus 1/2 x squared plus 13/6. And then we're done. Okay. Now, this class is more than one lecture for the following reason. This right-hand side could depend on y. Let's think about that for a second. Suppose you pour water from a vessel. How much water, the rate at which that water leaves that vessel is going to have to be dependent on how much water is still in that vessel, right? It's not going to flow out at a constant rate. So what you get here is the rate of change is in some way related to the original function, the volume of water in the vessel. This you cannot solve by just doing an integral. The reason why is because if you look at this, we get y equals the integral of x squared y dx. That's true, that's not false. But in order to actually solve this integral, y is a function of x. That means that we're going to have to know what y is as a function of x explicitly in order to solve this integral. But if we knew that, we'd already be done. Okay, so we can't do it that way. Gonna have to do something else. That's what the rest of the course is about. All right, so that about does it for today, and I will see you in the next one.